Hello friends. Hello friends. Welcome to aimstoday YouTube channel. In this video, we are going to discuss about IIT-JEE NEET Foundation Chemistry Chemical Bonding chapter. From that, valence shell electron pair repulsion theory. This valence shell electron pair repulsion theory is simply said Vsepr theory. Valence shell electron pair repulsion model of molecular shapes is a simple extension of Lewis' ideas and is surprisingly successful for predicting the shapes of the polyatomic molecules. Sedgwick and Powell proposed that for molecules and ions which have only single bonds, an approximate shape can be predicted from the number of electron pairs in the valence shell of the central atom. The outer shell of the central atom of a molecule may contain one or more bonded pairs of electrons and also lone pairs of electrons. For example, if you see some ammonia molecule, it has a pair of electrons which are shared between nitrogen and hydrogen atom, which are called as bonded pair of electrons. In that way, ammonia molecule has three bond pairs of electrons. At the same time, on nitrogen, a pair of electrons are existing which are not participating in the bond formation. They are called lone pair of electrons. So in this way, the central atom of a molecule may contain one or more bond pairs and lone pairs. Bond pairs and lone pairs were expected as equivalent, since all electron pairs take up some space and repel each other. Repulsion is minimized if the electron pairs are oriented in the space as far apart as possible. Gillips and Alum improved the theory to predict and explain molecular shapes and bond angles more exactly. Let us see the important postulates from this Vsepr theory. One among them is the shape of the molecule is determined by repulsions between the all electron pairs present in the valence shell of the central atom. A lone pair of electrons takes up more space around the central atom than a bond pair because the lone pair is attracted to one nucleus, that is on the central atom, while the bond pair is shared by two nuclei. It follows that repulsion between two lone pairs is greater than repulsion between a lone pair and a bond pair, which is turn greater than the repulsion between two bond pairs. So the repulsion between two lone pairs is much greater than the repulsion between bond pair and lone pair, which is greater than that of bond pair and bond pair repulsions. The presence of lone pairs in the central atom causes slight distortion of the bond angles from the ideal shape. If the angle between a lone pair on the central atom and a bond pair is increased, it follows that the actual bond angle between the atoms must be decreased. The magnitude of repulsions between the bonding pairs of electrons depends on the electronegativity difference between the central atom and other atoms. Double bonds cause more repulsion than single bonds, and triple bonds cause more repulsion than double bonds. Multiple bonds between two atoms count the same as single bond in predicting the shape because it does not matter how many electrons present in each direction. In studying molecular geometry, it is convenient to divide different molecules into two categories. The one of the categories is molecules in which the central atom has only bond pairs and no lone pairs. For example, BeCl2, boron trifluoride, ammonia, PCl5, and SF6 molecules. In these all molecules, the central atom has only bond pairs of electrons and no lone pairs on them. And second category is molecules in which the central atom has one or more lone pairs along with the bond pairs. For example, sulfur dioxide, ammonia, water, xenon tetrafluoride, etc. In these all molecules, the central atoms have bond pairs along with one or more lone pairs of electrons. Now let us see the geometry of different kinds of molecules which are having different number of bond pairs and lone pairs on central atoms. First among them, the molecules with two bond pairs and no lone pairs. So then the two atoms spread on the both the sides of the central atom. Then the shape will be linear shape and bond angle will be 180 degrees. So example for such kind of molecules are carbon dioxide and oxide. So here these double bonds are considered as one bond in predicting the shape of this molecule. And next, the molecules have three bond pairs and no lone pairs. Then three bonded atoms spread in the space in the trigonal planar shape around the central atom. And the bond angle will be 120 degrees. And the molecules example for this is kind are boron trichloride, boron trifluoride, etc. These only three bond pairs are there in central atom. So hence they are existing trigonal planar shape. Next, molecules with four bond pairs and no lone pairs. Then the shape of the molecule will be tetrahedron. And the bond angle between the atoms will be 109 degrees, 30 minutes, or 109 degrees, 28 minutes it is said approximately. And example for this kind of molecules are methane. Next, let us see one more. The molecule with the 5 bond pairs and no lone pairs. Then in this kind of molecules, three atoms will be in the same plane along with the central atom. One will be above the plane and the other one will be below the plane. This kind of geometry is known as trigonal bipyramidal, and the bond angle within the plane will be 120 degrees and above and below the plane will be 90 degrees. So two bond angles are existing in this kind of molecules. An example for this kind of molecules are PCl5. Next, let us see bond molecules with the 6 bond pairs and no lone pairs. So here, 4 atoms will be in the same plane along with the central atom, and one will be above the plane and one will be below the plane. And this kind of structure is known as octahedron structure, and the bond angle between the atoms will be 90 degrees. Example for this kind of molecules are SF6, sulfur hexafluoride. Next, the molecules with the 7 bond pairs and no lone pairs. In this kind of molecules, 5 atoms will be bonded atoms will be in the same plane along with the central atom, and one will be above the plane and the other will be below the plane. This structure is said to be pentagonal bipyramidal. And the bond angle within the plane, between the molecules of the atoms which are in the same plane, the bond angle will be 70 degrees, and above and below the plane, bond angle will be 90 degrees. So the example for the molecule of this kind of geometry is ion is given zirconium heptafluoride. And next, let us see the second category, that means with lone pairs. A molecule with two bond pairs and one lone pair. So if there are only two bond pairs, these two atoms in the linear shape along the central atom. But as presence of a lone pair of electrons, this will push the bonded pairs of electrons. So linear shape is distorted, we can say. This shape is called bent shape or angular shape. And here the bond angle will be less than 180. So this will be varied from molecule to molecule because, as we said, the repulsion between the bonded pairs and lone pairs will be vary based upon the type of atoms bonded here. Based upon the electronegativity of these atoms, it will be varied. So for example, if you say sulfur dioxide molecule, its bond angle will be 119 degrees 3 minutes. Next, a molecule with two bond pairs and two lone pairs. Then also we say the bond shape geometry, bent shape or angular shape. For example, molecule for this, if you take water molecule, there it has two bond pairs of electrons and two lone pairs of electrons on central atom oxygen. So here the bond angle will be 104 degrees 5 minutes. Another kind of molecule with two bond pairs and three lone pairs. So now here the three lone pairs will come into a plane along with the central atom, and the two bond pairs will be in the opposite sides of this plane. This is a linear shape because we consider bonded pairs not lone pairs in predicting shape. So they are in the linear shape. Bond angle will be 180 degrees. An example for this kind of molecules is xenon difluoride, XZF2. Next, let us see molecule with three bond pairs and one lone pair. If there are only three bond pairs, then they will be in the trigonal planar shape as we have seen earlier. But by the presence of one lone pair, that will distort the shape of this molecule into pyramidal shape, which is a trigonal pyramidal. And if you say example for one of the molecules, that is ammonia, in this bond angle is 107 degrees. And next, three bond pairs and two lone pairs. If you see Here, these three bond pairs will come into T shape. Hence, these molecules are called T-shaped molecules, and these two lone pairs are above this. So here, in the same line, the bond angle will be 180 degrees, and here the bond angle will be 90 degrees. So we say two bond angles 90 and 180. An example for this kind of molecules is chlorine trifluoride, ClF3. Next, molecules with four bond pairs and one lone pair. Then the shape we say as a seesaw shape, means three are in the same lane and one other two are like a stand. This is a T-shaped or sorry seesaw shaped molecules. And here the bond angle will be 120 degrees and here it will be 90 degrees. And example for this kind of molecules is SF4. Next, the molecule with four bond pairs and two lone pairs. If there are two lone pairs and four bond pairs, the four bond pairs will come in the same plane in the square planar, and one lone pair will be above and one will be below the plane. So the bond angle will be 90 degrees. And the example for this kind of molecules is xenon tetrafluoride. Next, molecules of type with one lone pair and five bond pairs. The shape we say square pyramidal, and bond angles will be 180 and 90 degrees. My example for this kind of molecules is ClF5. Next, the molecule with five bond pairs and two lone pairs. This is a pentagonal planar. All five bonded pairs will be in the same plane along the central atom. The lone pairs will be above and below the plane. So the bond angle will be 70 degrees. An example for this kind of molecules is xenon. It is given an ion, xenon pentafluoride ion. So thank you for watching our video. Please subscribe our channel and press the bell icon for receiving latest updates.